Hello and welcome to second lecture in our comprehensive course of machine learning, data science and artificial intelligence. Currently we are doing 16th chapter. That is, the name of the chapter is Advanced Feature of SEABORN Library. In previous lecture we have done about three types of plot: violin plot, swarm plot and strip plot. Now we are doing this visualizing statistical relationship with regression plots. Now this would require some discussion first. So let us at present first load at least the iris dataset. We know that iris can be directly loaded using internet from the SNS repository sns.load_dataset iris. Okay, so there is no need of pandas to import the library or read_csv. That is not required. Okay, and this is our iris dataset: sepal length, sepal width, petal length and petal width. These are four features or four independent variables, and using these four features you should be able to predict species. So we want to create a machine learning model using that. That would become a multi-class classification model. However, at present we are not interested in that classification thing. At present, suppose I am just interested in, say, two related features like petal length and petal width. Forget about this. Others may, suppose I can drop the columns. Okay, iris dot drop sepal length x is equal to 1, then sepal width x is equal to 1, and species x is equal to 1. So these three columns will be dropped, and only these two columns suppose remain: petal length and petal width. And I want to see if there is some kind of relationship between petal length and petal width across the species. That means for all three species, Setosa, Virginica and versicolor, is there any relationship like maybe say petal length increases then petal width also increases, or maybe petal length increases then petal width decreases, and that again, that whether that relationship is same for Setosa, Virginica and versicolor, or that relationship is different for Setosa than different for versicolor and Virginica. Suppose I say decide that for as petal length increases, petal width also increases, then next question would arise is that is the increase linear or a curved relationship, say a parabolic relationship like that. So you don't know at present. So what we can do is we can first plot a graph of only these two columns. Okay. Now as such we want to talk about reg plot, that is regression plot. So in the code example you will find this directly sns.reg plot. But to make the discussion first clear, I have instead of that commented out that reg plot line. And I am first plotting our well-known scatter plot, and for x variable I am taking this petal length, so this would go on x-axis, and on y variable I am taking petal width, so that will go on y-axis, and data is equal to iris. Rest of the things are our usual thing that we load iris data set. Then so now even these steps are getting repeated because up to loading we have already done, right? So then we decide the figure size, then we plot sns.scatter plot. I say again, I'm telling you that our aim is to learn about that reg plot, but what is regression that we want to understand first, and therefore I'm plotting scatter plot. So then the scatter plot, it will not be regression plot. First I should modify this, that it is scatter plot of petal width versus petal length. Okay, normally versus when you write, that means always whatever is on the y-axis, that is called dependent variable, and whatever is on the x-axis, that is called independent variable, and y versus x, that is called petal width versus petal length. Okay, and you can plot the graph, and the graph is obtained to be like this. Now in this graph I can at least see some trend that as petal length increases, that means as I move on the right side in this graph through various points, I have to move upwards, because as I move on the right side, say here, there are no points here in this region downwards. Okay, so actually points also go on moving upwards as the points go on moving rightwards in this graph paper. So that means it is clear that there is a increasing trend or relationship, positive correlation between petal width and petal length. Positive correlation means as one variable increases, x increases, y also increases. Not only that, but I can roughly say one thing, that roughly the correlation appears to be linear. In no natural or actual data set, all the graphs would come out to be exactly on a straight line. Like for example, perhaps we drew one graph of sales and profit, something like here maybe. So not this one, but not even in this, but in chapter 14. But that is artificial synthetic data set which we had created, and therefore it was yeah, this one. Okay, so here on x-axis month was there, and on y-axis sales was there. Now such perfect line you will never get, but here you can see one thing at least, that more or less the trend appears to be linear. Now the question is, if I want to get that line which shows the linear relationship between these two variables, this will at that time become my y variable, petal width, and this at that time will become my x variable, petal length, and I want to get a relationship between that y and x. what is the meaning of word relationship? Think about this situation. Okay, so this is the same graph I have tested from that only. You can see here. Okay, so same graph, petal width versus petal length. Now, y versus x relationship means if I see that the trend is linear, then I can say that there is some this kind of equation which relates y and x, petal width and petal length. But I will now not speak long words. I will just speak y and x because they can be any other variable. The discussion remains the same for every data set. So y is equal to beta 0 plus beta 1 into x, where this beta 0 is called intercept on x-axis, y-axis, and this beta 1 is called the slope of the graph, right? So then the question is, and this whole equation, if I can get any such equation, maybe some this kind of equation I can obtain with some actual values of beta 0 and beta 1. So that means what kind of equation I am expecting? Then I am expecting an equation like y is equal to, say, 0.9 plus 2.1 times multiplied by x. Then we say that I have solved my problem of getting what is the linear relationship, and this whole thing, that is itself called the model. So when we go on speaking a linear model, so what is the meaning of linear model? It is nothing but a definite equation or functional relationship between y and x. So I can say that y is a linear function of x. Y is equal to fx. So that thing is itself called a model, a mathematical or statistical model. Okay, and if I get one such relationship, indirectly what I'm saying is that I get the values of this beta 0 and beta 1. If I somehow manage to get the values of these two, that beta 0 is 0.9 and beta 1 is 2.1, then my problem is solved, because thereafter I can plug in any value of petal length and I can x and I can find corresponding value of petal width y easily. So even if I want to do something which is some petal length which is say 9 not shown in the graph, that means none of my actual data point will have that petal length. They do not have this petal length. My range comes from say around 0 to 7, okay, in the petal length. But suppose I am asked that petal length is 8, and what will be the corresponding petal width? Then I just have to put x is equal to 8 here, and I will get the corresponding petal width y easily. Okay, so then I can say that this equation is the linear model using which I can predict y for any value of x. I can predict y for any value of x. Now the question is how to obtain such a linear relationship. So will we do it by mathematical process like some equation solving and all that? Then no, we will not do it by mathematical process. In fact, we will use the data, and I have already explained this, that if original data set had 150 rows like this, total 150 rows and 5 columns, so 150 rows we will divide into some 80-20 percentage. So say 120 rows will become my train set, and 30 rows will become my test set. Then I will let the linear regression algorithm on that 80 train data set. At that time, this petal length and petal width both will be known. Remember, I am ignoring the other columns at present. I am just taking these two columns. So for the train data set, both are known. So using their values, the linear regression algorithm will learn some pattern. Learn some pattern means what? It will learn some values of beta 0 and beta 1, which are closely, which are minimizing the error. Okay, what is the meaning of minimizing the error? I am coming to that very quickly. But then the remaining, for 120 observations, this and this both are known. So I let my algorithm pass through each and every observation, and it learns the patterns, that if this increases this way, if this increases this way, like that. Okay, so then it learns the patterns, and then on the remaining 30 observations, which I call my test set, I just keep petal length. I remove the values in the petal width, or just one simple data set, only petal length, only one column, and I predict what is the corresponding petal width. Okay, and that will be added as a new column here instead of species, predicted petal width. So I actually had the actual petal width for those 30 observations also, which I call test set, but I do not allow my algorithm to look at those values. Instead, I ask my algorithm that take this 30 observations, these are the petal length, now give me predicted value of petal width. So it will give 30 predicted values of the petal width, and then I can try that I will use that linear graph for which the difference between predicted and actual value, these are the actual values for those 30 observations, okay, and the predicted values are what I am going to predict using my this kind of equation, okay. So then, or using my algorithm's knowledge of pattern what it has gathered from the train set, and then I will try to find the minimum value of sum of squared errors. This we have discussed earlier. So we take y predicted minus y actual, that is this, for this remaining 30 observation. Then we take y predicted minus y actual square, and then we try to minimize that. So any line which minimizes that, that is called the line of best fit. And when you find the line of best fit, at that time you say that your regression task is over. So what I am saying is that I have these data points. Now this is the linear relationship. Beta 0 and beta 1 are not known. But what will be beta 0 and beta 1 finally when they will be known? Then they are the beta 0 and beta 1 for my line of best fit. Because I am saying that these two variables are petal width and petal length. They seem to be having linear trend as one increases, other increases. But linear can be so many different things. For example, this can be one linear trend. Y is equal to beta 0, 1 plus beta 1, 1 x. That is some value, say 0.7 plus 1.9 x. This is green. So for blue, suppose blue equation, suppose I get this kind of line, okay, then I will find the error, or I will find the predicted values which are on the blue line and the actual values which are these dots. Then I will find the difference between them, and then I will find the square of difference between them, and then I will try to minimize that square of difference, because that shows the error. My predicted value, for example, here my actual value is this and predicted value is on blue line. Predicted values will always be on blue line because my model I am taking this. So then predicted values will be on blue line, and this is my actual value. So this much error would come, difference between this and this. That is this vertical height, that is y actual, minus this vertical height, that is y predicted. Okay, and I will do square of it. Square is required. Why? That also I have told you, because for some the difference is positive, but for some observations, for example these observations, this is the actual height, but the predicted height will be more. So sometimes our blue line predicts more, sometimes our blue line predicts less. So when you find the difference between predicted and actual, then sometimes it is plus and sometimes it is minus, and it may cancel out each other and give a false impression that the error is very less. So I don't want that to happen. So therefore what I am doing is I am squaring first and then adding them, and then I am minimizing. So that error is called sum of squared error, SSE. And we try to find several lines. In fact, theoretically, how many lines can pass through these blue colored dots? Then infinite number of lines can pass. So I next try this green line, okay, and maybe for this green line I try to again plot the linear graph. Again my actual points are the blue dots, but my predicted points are all on the green line. So I can find the error. For example, this is my actual value and this is my predicted value. So I can find the error, that y actual minus y predicted, and that would give me the sum of squared error. Okay, so sum of squared error for that particular green line, and then I try to minimize that sum of squared error. By which line minimizes that? So ultimately, suppose after trying so many lines, when I say after trying so many lines, all those different colors, or that means different values of these two constants, beta 0 1, beta 0 2, beta 0 3, and similarly beta 1 1, beta 1 2, beta 1 3. So after trying so many values of these constants, suppose I find this pink colored line, and for that pink colored line, suppose these are the values, and the sum of squared error, this quantity, is the minimum for that pink colored line. Then I will say that I will ignore my other colored lines, and I will only keep my pink colored line as my regression line. Okay, and that line is called the line of best fit. That is this line, this pink colored line, that is called best fit line. And whatever are the value of intercept and slope for that line, they are my beta 0 and beta 1. Okay, so intercept is what? Intercept is when this line intersects y-axis. So here it is intersecting at 0 only. Remember, it is not necessary that every line intersects at 0. For example, this gray colored line, if you see, it intersects at somewhere 0.4. But this pink colored line here, luckily, just it intersects at 0. So my beta 0 would be 0. And slope. Now what is that slope? The slope is the obtained by drawing one small vertical and one small horizontal. Then this angle which the line makes with horizontal, that angle is called theta, or alpha, or whatever symbol you want to call it, x or whatever. I am calling it theta. Then tan theta, that is the opposite side upon adjacent side, that is called slope. So here in my case, what will be tan theta? Suppose this triangle is named A, B and C. Okay, so then in that case, tan theta would be equal to opposite side, that is AB, divided by adjacent side, that is BC. Okay, hypotenuse you don't have to consider as opposite or adjacent in a right angle triangle. So opposite side upon adjacent side, AB upon BC, that will give me the slope. So in short, once I get my pink colored line, or the line of best fit, or the line which minimizes the sum of squared errors, then I just have to find its intercept, and I just have to find its slope. That will be my beta 0 and beta 1. Once I put them here, then whatever equation is obtained, this is itself called linear regression equation between y and x. And then this equation can be used to predict the value of y for any different value of x. Is that clear? Okay, so then this is the situation. This is linear regression equation, or in simple word we call it model, regression model. Okay, now the question is, will we have to draw many lines, and will we have to then measure the sum of squared error for each colored line, and then will we have to measure beta 0 and beta 1 for each colored line and then choose the line of best fit? No, no, everything is done by the code itself in a single line. Okay, so therefore that is the feature which we now want to study. So we want to see that a regression plot will automatically not only plot these dots, that is scatter plot, but it will also plot a single line that will be the line of best fit. Okay, so first I plotted I commented out this reg plot line, and I just plotted my scatter plot so that I can do all this discussion. So now it is clear that I want to find one line for which the sum of squared error is minimum, or in very common language I say that I want to find one line which is closest possible to majority or almost all of the data points as a whole on aggregated basis. Correct? So now I am commenting out that scatter plot because my aim was not to learn scatter plot, but my aim was to learn reg plot, regression plot. So if I plot it, SNS has this fascinating ability that it will automatically find that line which is the line of best fit. Okay, and not only that, this shaded region is also shown. It shows that here there is hardly any width of that shaded region, but as you go on this side, right side, further and further, you can see that the width of that light shaded region that goes on increasing. So that region is called confidence interval, because these are statistical models, so they are never 100% accurate. There is always a 5% or so variation in statistical models, right? So depending upon how much accuracy you have decided and how much accuracy is inherently possible for a given data, so this is called width. This width gives the confidence interval. Here the width is say plus or minus 1%. So that means whatever the blue line gives and the actual values of the data point, they may differ by around 1% at the most. But here suppose the width is plus or minus 5%, then you will say that the actual value and the predicted value of the data point, they can differ at the most 5% in this region. At the most. Now some can differ by 5%, some can differ by less than 5%, this is differing by less than 5%, but around in this region, maximum deviation from the actual point would be 5%. You can see one thing, that as I go on moving further and further, mentally extend this line, then that region would go on going wider and wider, right? So that means that confidence interval, or you can say the accuracy of my model goes on decreasing, in my sense that the region plus or minus 5%, here somewhere it will become plus or minus 6%, here somewhere it will become plus or minus 8%, like that. Okay, so this much, whenever I plot line passing through all the data points of my given data set, that is called interpolation. And this much in this region, if I extend my graph by say a dotted line for some petal length, say 9, I am trying to predict petal width, but there is no petal length 9 in my entire 150 rows. So that means I am going beyond the range of my data. So at that time, I can predict, my predictive model will predict if I assume that this will continue on a linear path. But the error in the prediction, that will go on increasing, because this light shaded portion, that will go on becoming larger and larger. Okay, so that is about this scatter plot between one numeric variable and another numeric variable. And if you don't want to plot scatter plot, then you can plot directly the reg plot, so that you can directly show that this is the line of closest fit. And remember, every data set will not have such linear trend. It is possible that the points are distributed somewhat like these, or maybe somewhat like this curve, or even circularly, a circle will be there. So any distribution can come, and therefore linear graph will not always be possible. Okay, but in this case, and this is a natural data, for natural data set, you get a linear regression plot. Okay, now we will extend this linear regression concept. Okay, let us extend here only, because continuity will be unnecessarily broken. So this is the, here I have taken x and y as this petal length and petal width, right? But what about other pairs? So I have taken the pair of this with this, but there are total 4 numeric variables. So I can take a pair of petal width with sepal width. Okay, I can also take a pair of petal width with sepal length, and I can also take a pair of sepal length with sepal width. So total 4 different pairs would be possible between this, in fact, sepal length and petal length, and several combinations are possible. So what I am saying is that if I want to see similar trend for the other numeric columns, and I don't want to plot, one method is that here only instead of petal length, I just copy paste this word sepal length and put it like sepal length, and similarly instead of petal width, I put this word sepal width, and I put here this sepal width, correct? And then I again plot the graph. The question is, do I need to do same thing again and again, repeatedly? You can see here there is not much a linear relationship. Okay, the points are almost randomly scattered. The reg plot tries to fit a straight line, but you can see the error is very large between actual data point and the predicted data point. Now my point is that Do I need to plot a different graph each time by for different numeric columns? Then no, there is no need. I'm bringing the original graph back. Okay, there is no need of plotting different graphs. In fact, I can plot all the graphs on in one only, but for that I have to use this. One is I have to use subplots, so that multiple plots can be plotted on one. This feature we have already learned earlier also. And we have to use sns.lm plot. The lm plot means linear model plot. Okay, and I again take the same two parameters, petal length. Sorry, I take different parameters now. Here I have taken, oh yeah, petal length and petal width. So same two parameters, petal length and petal width. But I want to do for all the species. So I made some mistake in the explanation, previous one. That also you can do by that kind of copy pasting the code and just changing the name of the parameter, or you can do by a for loop and you can make a combination of two parameters, linear parameters at a time. But here I want to plot a graph of same petal length versus petal width only, but I want to see if the graph is nice linear for setosa also, for virginica also, and for versicolor also. This is actually a general graph for entire data set, but in my entire data set there are three different types of species, or three groups are there. So I am asked that plot similar reg plot for each species separately. Now what I will do, will I split my data set into that part? I can do that also, that horizontal split with condition that species is equal to setosa, that will give me df1. Then again next is condition species is equal to virginica, that will give df2. And then next will be species is equal to versicolor, and that will give me the other df3. And then here, instead of data is equal to whole iris data set, I can write data is equal to df1. These two remain same, but data set will be changed. df1 for only setosa, df2 for only virginica, and df3 for only versicolor. Then three separate plots will be obtained. But there is one good feature that is called lm plot, and in lm plot you just have to add one variable extra. So if you compare the syntax, let me clear this graph for a moment. Okay, so if you compare the syntax, then here also reg plot had x, what variable you want to take on x-axis, here also x, y, what variable you want to take on y-axis, here also y. Then data set name, so here also data set name is full. I will take full data set, but I actually don't want to plot for the entire data set. I said that I want to plot for one line for setosa, another line for virginica, and another line for versicolor. Okay, and I want to see that the linear relationship which I got in this that was the same, that will remain same across the species, or that will go on changing. So then in that case I just have to add one more extra argument. This argument x, y, and data remain same as reg plot, but when I plot sns.lm plot, so at that time column is equal to species. Remember, this is not color but column. So that means three column graph will be plotted. First column will have species equal to setosa. Next linear graph will be plotted in the middle column, that will have species equal to say virginica, and next will be on the rightmost column, and that will have species is equal to versicolor. These rest of the things are okay even if you don't write them. Aspect is equal to this much and height is equal to this much. Your plot will be plotted. So for example, let me just remove it. Okay, because why unnecessarily make things complicated? So only essential matrix or only essential parameters I am writing, and this is the graph. Now you can see this is the graph for setosa, this is the linear graph for versicolor, and this is the linear graph for the virginica. So all species have more or less linear relationship between petal length and petal width. Okay, but the line are inclined at different angles, and lines are inclined at different angles means this theta will be different for setosa and virginica and versicolor, and therefore this tan theta, that is this beta 1, the slope of the graph, that will also be different for each of this graph. So if I want to fix linear model, create a linear model, then I will have to create three linear models, one for this species, one for this species, and one for this species. I cannot fit one common linear model like this for entire data set. So this much gave me an idea that okay, these two, petal width and petal length, for entire data set appear to be linearly related. But this gave me better idea that okay, they are linearly related between petal width and petal length, but they are having different beta 0, that is intercept, and they are having different beta 1, that is the slope. Okay, so that much is clear. Now here is the difference between reg plot and the lm plot. So in reg plot, it plots actually just a scattered data and linear regression fit. It is scattered data and linear regression fit. While this lm plot, linear model plot, combines reg plot with a facet grid. This is called one facet, this is called another facet, and another facet. So three facets, or if more categories are there, 10 categories are there, then it will be 10 facets. And it plots conditionally. Conditionally means I said that from this you can select the rows conditionally, that select only those rows where species is equal to setosa, select only those rows where species is equal to virginica, and so on. Flexibility point of view, this accepts one axis object for the plotting, while this creates a figure and sets up grid for the plotting. So it is a slightly different way. Here this subtitle word is also important. Common source of mistake is here people write subtitle. So it is not subtitle but subtitle. Okay, SUP. Now then here control, then more control over the specific axis which are used is there with reg plot, but manages figure setup and offering less control. It manages on its own, and therefore there is obviously less control by you to customize this plot. It automatically manages. You just specify that I want three graphs separate on the basis of species, and it manages the x and y axis and the scale on the y axis and everything on its own. But therefore flexibility or customization flexibility will be less. Use case will be whenever there is a simple linear fit within a single plot, that is in a single category. Suppose I have isolated only Setosa species data points, and I want to find a linear regression plot for them. Then obviously at that time SNS.rect plot is better. But use case for LM plot is it is exploring category relationship across categories. So that means here three categories were there: Setosa, Virginica, and versicolor. And if I want across all these three species, then I just add one variable column is equal to species. So first column, second column, and third column will plot the graph for different species. Layout management is done by automatically. While here, here you can configure. By here you can't configure much because you have to leave it to handle. It will take the data set. It will divide the data set internally into three species. It will fit a line for each species. It will select appropriate scales, and it will draw the plots for three species separately. So LM plot is very powerful, and it can work for any number of species, 10 species or 20 species, okay. But then it will adjust so many things on its own. So therefore, it is not customizable. Layout is not customizable. This reg plot, its subplot command does not support faceting, while LM plot supports faceting by splitting data across categories. Okay, so that is the reason why here this subplots underscore adjust and subtitle that is written. So faceted data is created. The faceted plots are created using this. In next lecture, we will be doing this. We are stopping for now. Thank you.